Jelena, feel free to go ahead and we will enjoy the talk.
Thank you very much, Dimitri, for your kind introduction and for the invitation. And although you may not know that, but I have Australian connection. Before going to Caltech, I spent 6 months at the University of Sydney doing research on error correcting codes. So it's actually a great pleasure to speak to Australian researchers because I really enjoyed my time there. I will talk about scalable semiconductor, quantum, and classical photonic systems. This is a little bit different from the title I sent to Dimitri originally, but I thought that this would actually capture more precisely what I will be talking about today. And basically, I will start by saying a few words about our work on building scalable photonic systems, which is applicable both to classical and quantum photonics, and then specifically talk a little bit more about our quantum photonics work. So photonics, as you know, has many interesting applications today. These are some that my group is interested in. There are also many more. Optical interconnects for data centers, quantum technologies, augmented reality glasses, a variety of biosensors, sensors like LiDAR, optical neural networks, and other computing platforms. But basically, for implementation of all of these exciting applications, we actually need integrated photonic solutions. So you need to pack a lot of different devices and components into a very small footprint because free space optical solutions like the one on the left would not really work. You have to fit something in a footprint of glasses or portable devices or small chip that you would mount as a sensor on your car. So how do you go from what you see on the left to integrated photonic system that you see on the right? And of course, people have been working on integrated photonics for decades now, but still traditional kind of mainstream integrated photonics solutions are not really optimal for many of these applications because there's a limited number of functionalities, efficiencies are limited, you need to fine tune and tweak a lot of different devices to build the scalable systems. And actually photonic integrated circuits are nowhere near electronic integrated circuits scaling today. So around 15 years ago, in my group at Stanford, we decided to look into this problem and simply try to answer the question of whether we could design and make better photonics. And by that, we mean better photonics devices than what we know today, with smaller footprints, higher efficiencies, robust to fabrication errors, temperature variations with new functionalities, and can be kind of eliminate brute force design and manual parameter tuning from the design process so that even electronics designers, circuit designers could design photonics, which is often necessary because you need to build complex systems that are composed both of electronics and photonics. And about 15 years ago, we managed to finally design three-dimensional photonic devices, which was very important because you can only in 3 dimensions capture the full behavior of the system. And the main idea here is to search the full parameter space of all possible solutions until you find something that satisfies whatever function, kind of input to output mapping you would like to achieve. And what is very exciting in this process is that you can really address all of these goals that I mentioned previously, smaller footprint, higher efficiencies, and so on. But often, even for some of the functions for which we had some state-of-the-art solutions, you can obtain much better solutions, and they are completely non-intuitive. So for example, what you see here is a wavelength splitter. This is an optimal wavelength splitter for 2 different wavelengths, and it's kind of at least an order of magnitude smaller in size than the way people would traditionally do filtering or wavelength splitting with some resonators coupled to waveguides. It's also robust to errors in fabrication, temperature. So it's really exciting to see that there are many solutions that are much better than state-of-the-art. And although you restrict footprint to something that's at least an order of magnitude smaller than smallest wavelength splitters out there, it turns out that even in such a small footprint, there are multiple solutions that are very efficient and have the right performance. So this is how it started, right? And these are actual fabricated structures in silicon. But of course, over time, we moved on to more complex systems that I'll be talking about today. So these initial structures that we focused on were wavelength splitters, mode converters. Here you see 2-channel wavelength splitter, 3-channel wavelength splitter, and these are actually actual fabricated structures in silicon on insulator with superimposed electromagnetic fields. The one on top splits 2 wavelengths in a footprint of 2.8 by 2.8 microns. The one at the bottom splits 3 wavelengths in the footprint of 4 by 5 microns. And when I say it performs particular function in a smaller footprint, it also does it with the efficiencies that are comparable or sometimes even better than for traditional devices. So that efficiency, high efficiency, is part of the design process. And what you see on the right is the measured performance of these structures. And what is also super exciting is that here we show measured performance for many devices that are fabricated with the same parameters in our university laboratory. And then we just plot transmission for all of them without any post-tuning. And they all line up on top of each other without any post-tuning, which is not something that you achieve with traditional photonics, where you always need some heaters and some tweaking elements to tune them on resonances with each other. So the fact that you can design devices to be robust and sensitive to the environmental and fabrication errors is really important, because the yield of functional structures is much higher. And that's really what you see here, because here you have really transmission plots plotted for many devices that we made at Stanford, and our fabrication process is certainly not perfect, and neither is fabrication in a foundry or other fabrication facilities, but we can reliably fabricate them to exhibit particular performance because we designed them to be robust. So that was, again, really exciting development for us, because we could design it in 3 dimensions, and also we could design them to be robust and have higher efficiency, smaller footprint, and so on. But since these initial devices, demonstration of initial devices, we moved on to more functional systems over the years. New functionalities, here are some examples of new functionalities we demonstrated, including non-reciprocal pulse routers in silicon photonics, particle accelerators. This is on-chip laser-driven particle accelerator. I'll say a few words about it. I mean, this is sort of ultimately new functionality using photonics for high energy physics experiments or applications. Then we also moved into foundry, essentially fabricating complex circuits consisting of many elements, photonic elements, in commercial foundries. And I'll also say a few words about that as well, because of course you want to move out of university fabrication facilities if you want to fabricate complicated, complex systems. This is really very exciting for us, because we showed that the process is also fully compatible with commercial foundries. And also, although the examples that you see on top are all silicon on insulator, and commercial foundries are basically silicon foundries these days, I'll also show you a lot of exciting examples from my group on other materials, because the process of inverse design is agnostic and it can work on any material. So we worked also a lot with diamond and silicon carbide for quantum photonic systems, and I'll describe that in a moment. And since we worked on this for many years, we developed software suite, which we call Stanford Photonics Inverse Design Software, or SPINS. This software can be licensed from Stanford, and many companies and research groups around the world are using it. We also have open source basic version that we call SPINS-B, and that can be downloaded from GitHub. So that's a basic version of the solver, and doesn't contain all the features of the full software, but still a lot of people are actually using it and playing with it. And I should mention that software is basically composed of very fast electromagnetic solver that we wrote, so that you can solve these problems in a short amount of time, orders of magnitude shorter time than commercial electromagnetic solvers, and also fast optimization tool. So for example, something like this, that is several microns in each dimension, in 3 dimensions, would require maybe hundreds or thousands of simulations in series as you're doing optimization, and we can solve all of that in something on the order of a few hours on gaming GPUs. So we made software that doesn't really require supercomputers. You can just use kind of inexpensive gaming GPUs that cost a few $1,000s, and you can solve this in a couple of hours. So if you're doing electromagnetic simulations, you know that generally for something of that size, if you use some commercial tools, you would need much more time than that for 1,000 simulation series. But doing it fast is very important, because you have a feedback on your optimization process pretty soon. So that's kind of where we have been going with that. And let me now give you some of the recent results. I'll give you few recent results that are showing the power of using this tool for new functionalities or integrated photonic systems, and really ultimately new functionalities, particle accelerators. And you are all familiar with how particle accelerators look like. Generally we imagine them as something like this. This is linear accelerator that is on a hill next to Stanford, few miles long. Stanford Linear Accelerator, of course, there is LHC and CERN, and state-of-the-art accelerators are always these gigantic structures where you use microwaves, radio frequency waves to accelerate particles. But the idea here in this work that is a part of a large international collaboration, ACHIP, that we're part of, which is led by Bob Bayard from Stanford and Peter Helmenhoff from Germany, is really to move to using optical frequencies, infrared light, to accelerate particles. Again, these are just electromagnetic waves with much smaller wavelengths. And then by the wavelength scaling argument, if you go to wavelengths that are 10,000 times smaller than traditional wavelengths used in accelerators, you should be able to shrink the accelerator as well. So you can go from 3 miles that you have for Stanford Linear Accelerator 10,000 times down in size, which means that you can actually implement this on something on the order of 1 inch or a few inches on a silicon wafer. And that's actually really exciting because it brings you to a completely new regime where you could, in principle, build accelerators that are much more accessible, right? People don't have to come to one facility from all over the world to do imaging and material science experiments, or even for medicine, it would be much more accessible to have accelerators, medical accelerators that are used for irradiation, cancer radiation. In principle, every lab around the world could have an accelerator, and the cost would be much lower because the main cost would really be a laser, right? Outside laser that you couple to accelerator. Other than that, it's all a chip. So how do you get there, right? I mean, the idea is pretty simple, but you can't just take traditional accelerator and shrink everything down by 10,000 times because it wouldn't work, right? The components that you have for radio frequency waves and microwaves would simply not work. So you have to build everything out of dielectrics. And how do you build structure that would accelerate the electrons once you couple these infrared waves? I mean, it's not a trivial problem. It's nothing that people have solved before. People tried with some photonic crystal structures in the past, but it didn't really work very well. So we rely on inverse design, on optimization. And here you see how the optimization process looks like. We're basically designing a stage of accelerator in such a way that for an electron that's coming from here in vacuum, it would always experience the field in phase with it as it's moving through the structure, so that it's always getting a kick in the right direction and being accelerated. And as you're doing optimization on that figure of merit, you are obtaining this permittivity distribution shown here, and also corresponding fields are shown here. So for the incoming electron with a particular energy, velocity, it's always getting accelerated. And the structure, of course, looks non-intuitive. It's computer generated for a particular figure of merit, but it works really nicely and really well, as you see from the experiments in a moment. So the final structure is shown here, right? So you shine light on a side, you couple it, I'll show you the full system. Again, this is just a single stage of accelerator that would provide some kick to electron. And then, like in traditional accelerators, you cascade thousands of stages until you get to very high energies, relativistic energies. This is how the field would look like. Your electron would pass through this vacuum channel here. This is all in silicon. Here we are coupling 2 micron wavelength infrared light. But we are also doing experiments with 1.5 micron, again, infrared light. And here is the fabricated structure. Again, this is a channel for electron, and here you see superimposed electromagnetic field, and this is in silicon. So then when you build the whole system, that's the stage, which is 30 micrometers long. This is the coupler for light. That light is coupled, guided here, goes to the stage of accelerator, 30 microns long. And then here, electron is coupled from the source. It has 83.4 kilo electron volt energy. It's coming from a converted scanning electron microscope. And we do experiments and check whether when we turn on the laser, we actually accelerate these electrons. We provide additional energy to electrons. And here you also see kind of zoomed in version of this picture. So what is interesting is that here we really have 10,000-fold reduction in size of the stage of the accelerator. This is just a single stage, but you can cascade thousands of them, and in about 3 centimeters, you should be able to reach something on the order of mega electron volt energies, starting with 80 kilo electron volts. So as you see from in a moment from the experiments, we have an acceleration gradient of 30 mega electron volts per meter, which means that, you know, when you multiply with the length of these 30 microns and 1,000 stages, you should be able to reach mega electron volt energy of these electrons that are coupled with only 80 kilo electron volt energy. And mega electron volt is already interesting for some imaging experiments, material science experiments, or irradiation therapy. So we're very excited about this and looking into scaling things up. So here is the experiment. You know, you have everything fabricated, you just clear it out single stage so that you can couple your electron beam. And then you look at the energy of the electron at the output when you have laser on and laser off. Without the laser, you just have the output electrons that have the same energy as the input. Nothing really happens in the structure. They just enter with the energy of 83.4 kilo electron volts and exit with the same energy. But when you turn the laser on, then you accelerate them and you provide a little bit of a kick to those electrons of about kilo electron volt. It doesn't sound like much, but keep in mind that that's only 30 micrometers of a structure. And that kilo electron volt per 30 microns converts into 30 mega electron volts per meter, which means that if you provide a kilo electron volt in each stage and you go through 1,000 stages, you'll get to mega electron volt energy. So that's kind of the ultimate new functionality enabled by inverse design. And what we're right now doing is we're moving this to commercial foundries and trying to scale multiple stages, thousands of stages of accelerators, and reach those interesting energies of our interest. And as another kind of recent result of large scalability that we can achieve in a foundry, I will not really go into details of this result. It's a completely different application, and this is a work that was done in collaboration with our colleagues from Stanford, UPenn, UC Santa Barbara, and USC on optical interconnects. And optical interconnects briefly are just optical connections that are replacing copper wires in either chip-to-chip connections in computers, and they're of course already used to connect different computers in data centers. And the reason for doing that is to reduce energy consumption and increase the operating speed. You all know the data centers actually are consuming a lot of energy, and everybody's trying to address that problem. And we also all know that our laptops and computers heat up, so we're trying to address that by reducing energy consumption and reducing loss by using optical connections. You know, there are a lot of problems here, and people have been working on this for a couple of decades. And in particular for chip-to-chip connections and on-chip connections, like processor to memory and so on, there are a lot of unsolved questions, and a lot of people in industry and in academia working on these problems because, you know, we all know that photonics has much larger scales than electronics, and it's very sensitive to the environment. So when your electronics heats up, then photonics doesn't really work very well, and there are no solutions for a lot of problems that we have to solve. But we've been able to, again, use inverse design here to achieve a very large aggregated data rate of 1.28 terabits per second with very small bit error rate, more recently smaller than 10 to minus 12. And, you know, this is actually really exciting for us, and I'm more of a fundamental researcher, but I'm mentioning this because this is already in the range where it could be practically applied without any correction, used in data centers for communications with much lower energy consumption. And how this works is basically implemented in a commercial foundry. I mean, this is how the chip would look like. You are converting electrical signals to optical signals using some sort of modulators at different frequencies, and then you are combining different frequencies in different spatial modes, and that's what we enabled with inverse design. And then in this case, you are using this for on-chip communication via this multi-mode waveguide that is a few hundred micrometers long, but we also did for chip-to-chip communication. And I'll show you the zoomed-in version of this inverse design element. Again, this is all fabricated in a commercial foundry. Here are the inverse designed elements that we use. in order to combine different inputs and translate them to different spatial modes at the output. And the reason why we're doing this is because it enables you to increase the number of channels for communication, as opposed to kind of traditional approaches where people use only wavelengths to encode different communication channels. So here, in addition to wavelengths, you can kind of use multi-dimensional communication because you also have spatial modes, and you can multiply number of wavelengths with number of spatial modes, which increases your communication number of communication channels dramatically. And this problem prior to this had not really been solved really well, because it's very difficult to perform multimode communications on a chip. But we managed to do it with inverse design elements. Then, again, if you look all of this, they kind of all look alike, like the one behind me or this one here, but they have very different functions. This one here really converts different inputs in 4 different channels here to different spatial modes at the output, with high efficiency, high bandwidth, and large contrast between different ports. And finally, I got another kind of interesting example, which has relations to communications, but also both classical and quantum communications. Optical vortex beam emitter. People have used these optical vortex beams for multimode communications, but also for hyperentanglement in quantum communication. And here we show how experimentally you can convert different inputs from your on-chip waveguide to different angular momentum beams at the output. Again, this has not really been done in this particular configuration from on-chip input to the output, but we showed that our experimental output, which is in the top row, can be pretty much matched completely with the desired theoretical output. And when you shine your input beam from your on-chip configuration onto this silicon outcoupler, you would basically, in the vertical direction, produce these different angular momentum modes, right? And this is just designed to satisfy particular function with in really high bandwidth. Again, different from traditional solutions. You can use it in a large range of wavelengths. You can also go beyond that and kind of multiplex different inputs. You have something where for excitation from this direction, you produce L equal to -1 angular momentum mode vertically. For excitation from the right, it's L equal to +1. For excitation from the bottom, is L equal to 0. Or when you excite all of these at the same time, you can have superposition of these different angular momentum modes. And not, to the best of my knowledge, nothing like this existed before, but you can actually easily design this in the order of a few hours. So that's kind of illustration of the power of this, how you can design things for new functionalities, for foundry fabrication, for integrated configurations, for even kind of ultimately new functionalities such as on-chip laser-driven particle accelerator. But now I would like to shift gears and spend time until the rest of my talk talking about quantum systems and how this relates to quantum systems. And I think this is probably a good point to see if there are any questions about the previous part of the talk and inverse design in general, because I will be talking about quantum systems in diamond and silicon carbide from now on. Are there any questions?
Do we have any questions? Okay, I have a question. So
yeah, sure.
If you could do accelerator of the pocket size, could you do the collider to?
Well, I mean, I think this is an interesting question, right? For accelerator as well, right now we're just looking into lower energies, something on the order of mega electron volts, right? And modern high energy physics experiments are at much higher energies, of course, right? And colliders as well. It's not completely clear what the limit is. I think the limit on right now comes primarily from material damage, because we're trying to address efficiencies of coupling of light and peak materials that are working the best, for these particular wavelengths. And sometimes it's interesting that kind of silicon always turns out to be the best material for a lot of things, because people have perfected, growth of silicon, right? It has fewest defects, which is why it's works the best. It's most resistant to high power excitation. But ultimately, even when you prove all the different elements, we would be limited eventually by melting of the material or damaging the material. And that's also what happens now, right? We are, and eventually, if you want to accelerate more, you need to also couple more laser power, and we're burning and melting structures right now. If we keep increasing it, we could actually increase the efficiency somewhat, but there would be a limit to that eventually, which would actually give the limit on the energies that you can achieve for accelerated particles, which may, not make them useful for modern high energy physics experiments and colliders. But who knows? I think that's where we are right now, and we're just thinking of some, modest energy range for medical applications or imaging. But maybe going forward with different materials and, with improvements, it could also be potentially interesting for higher energies and high energy physics, kind of state-of-the-art high energy physics, and also collider.
Yeah, it would be great to have Large Hadron Collider on the table.
Yeah, who knows? Not yet there. I think for now it's mega electron volts, right, or that range. What we're shooting for.
For the beam, in the sketch, there's a straight line. So if it is material, it could scatter on impurities, phonons, or anything else. Would one expect that it diffuse or could be bended?
Oh, are you talking about instead of making linear accelerator?
Yes.
Yeah, different configurations.
Yes. In accelerator, it is in a vacuum. In a vacuum.
Yeah. You could actually, I mean, of course, what we showed so far is just a single stage of the accelerator. And of course, going to next stage, you would have to adjust for the incoming energy and redesign the structure and adjust for that. Yeah, in principle, I mean, in combination with some magnets or some other external structures, you could imagine that you could also, or different types of photonic structures, you could imagine that in principle you could also do other types of geometries, not necessarily linear geometry. We haven't really thought about it yet, but I mean, thinking just in general about this, it's all electromagnetic waves. So if you can design things that microwaves and radio frequencies, you should be able to design it also with the electrics at optical frequencies.
Okay. Yeah. Thank you.
Thank you. Irina also has a question. I see her raising hand.
Yeah, thank you very much. Very interesting talk. I had a bit of question. Could you talk a little bit more about design of that optimization function? Which can achieve such an amazing outcome of structure that seems so random, can achieve so much determined and stable outputs?
Yes. So that's an excellent question. And the figure of merit that you are optimizing for or designing for, of course, depends on the problem that you are solving. And if you're really interested in this, I would really refer you to, review papers we wrote. There was a recent paper we wrote in Applied Physics Reviews, or their theses on my students on our group site, and instructions also on the GitHub also for different problems that we suggest to people to solve. But of course, the figure of merit or whatever you are optimizing for depends on the particular problem, right? So if you are looking at the structure behind me, which is a wavelength splitter for two different wavelengths, kind of broadband, with high efficiency in a small footprint, your figure of merit would basically be a combination of transmission of, this wavelength to top port, this wavelength to the bottom port. You want to minimize crosstalk, so we also kind of include that into figure of merit. But all of that, goes into the figure of merit. And then also, since we do fabrication constraint optimization, we also include there sometimes minimize, introduce robustness to kind of feature changes by certain amount, or temperature changes by certain amount. But you're building up, basically, depending on the problem that you're solving, this function that you are optimizing as you are going through kind of your complex parameter space. And then you're calculating essentially in each step of optimization the sensitivity of that function on parameters of the structure. And that's kind of gradient calculation, like gradient descent, but it's a multi-dimensional gradient descent. And to do it very fast and efficient method, we use something called adjoint optimization. And that tells you which kind of structure features in the structure to change in order to converge this sooner towards your local optimum. So it's really like a gradient descent. You know, I'm sure you know gradient descent in one dimension at least when you're going to a minimum or maximum of a particular function. But it's the same thing, but in a high dimensional space, and it's constrained by whatever parameters you want to constrain. So again, we talk about it in a lot of our publications, and there is no unique figure of merit that you're optimizing. It depends on the problem that you're solving, and depends on the material and fabrication constraints and so on. But you can build it up for a particular problem always.
Thank you. Very interesting.
Thank you. Okay, so are there more questions, or we can move on to the second part? And of course, you can ask me about the first part later on. But I thought that this would be a good place to ask for some questions. Okay. So let me move on, and I know that there is, of course, a lot of interest in this community regarding quantum systems. And now I'd like to spend time talking about that, which is really answering this question of whether we could build scalable semiconductor quantum networks, sensors, simulators, and computers. And of course, these are all the pillars of quantum technologies, and there is a lot of excitement about it. And these days, there are some interesting superconducting quantum systems that are showing quantum advantage, like the superconducting systems. This is a superconducting system from IBM, but of course, there are others from Google and so on. Atomic simulators consisting of a few hundreds or even thousands of qubits, like this one from Max Planck in quantum optics in Munich, Manuel Bloch's group, but of course there are also systems at Harvard and MIT, like this one and at other places throughout the world. And we're really interested in whether we could put these systems on a chip and really build them in a kind of more scalable manner, and instead of working in dilution refrigerator or having this complex atom simulator shown here, can we actually put everything on a footprint of a chip and simplify at least all of the overhead that goes into building of that quantum simulator or quantum computer? Of course, working with solid state systems, we don't need trap for atoms or ions anymore. And we also don't need to work at dilution refrigerator temperatures. And we have worked with systems that have direct optical interface. So that kind of reduces the overhead around the system that we're working on. And we rely on kind of traditional semiconductor processing in implementing these systems. And I will be talking about how we think about this and what we're doing. And often people think about these semiconductor systems as essential systems of quantum networks or quantum sensors. And of course, there was recent beautiful work from Delft, Ron Hanson and Stephanie Wenner on implementing 3-node quantum network using core centers in Diamond. And that's still very similar platform to the one that we are using, but we're really interested in, going even beyond quantum networks and quantum sensors. There are somewhat natural applications of these systems to implementations of really scalable quantum simulators and computers. So that's the question that we'd like to answer. And really, people often talk about these different applications, different quantum technologies as completely separate applications and separate directions of research. And indeed, there are some platforms that are more suitable for one direction than the other. For example, superconducting systems are suitable for quantum computing or simulations, not really very useful for quantum networks and quantum repeaters because they operate at microwave frequencies. Or people often think about semiconductor color center based systems as very suitable for quantum networks, but not yet scaled to the interesting scales of quantum computers or simulators. But in reality, if you have a platform where you already have homogeneous, long-lived qubits with good optical interfaces, and you have efficient optical connections between those qubits using photons, in principle, you can actually implement all of these different pillars of quantum technologies. You could use that platform to implement both quantum network and quantum computer and quantum simulator. right? So that's really where we're going. And the platform that we are interested in are optically interfaced semiconductor spin qubits. So really for us, qubit is a spin of an electron that is bound to an impurity in semiconductor. And there is, of course, a lot of beautiful work on using spins as qubits in semiconductors. In Australia, there is some of the leading research in the world in this particular field, but we're specifically interested in optically interfaced semiconductor spin qubits, not electrically controlled, but optically interfaced. And the reason being is that that platform is very natural for connection, of course, of our networks and building distributed quantum computers and quantum networks. And of course, also my background is in optics. We also like to interface things optically, but there is a natural application, which means you don't need any quantum transducers or anything like that in order to network these systems via fibers or even free space connections. So again, for us, a qubit is a spin of an electron, which is bound to an impurity in semiconductor, for example, diamond or silicon carbide, and it's optically interfaced. And then we build optical structure around that in order to interface it better optically and collect those photons that are used as an interface. And if you think about this system, if you think about this impurity inside of a optical resonator or optical structure, physics of this is exactly the same as an atom in an optical cavity or ion in an optical cavity or microwave or superconducting qubit Josephson junction inside of a microwave cavity. Equations are pretty much the same in the regime that we're interested in. But there are differences, right? So if you're thinking about superconducting qubits, of course, they're much larger. Again, they operate at microwave frequencies. You're defining qubit yourself lithographically, so you can make them in principle to be all the same, but you're working with superconductors, you're working at microwave frequencies. You can't map them to optical photons right away. You need quantum transducers. There is no direct optical interface. On the other hand, for our system, we work with semiconductors. We can operate at higher temperatures. We don't really need dilution refrigerators. You can work comfortably at few Kelvin temperature. There is already excellent optical interface. And maybe most importantly, the number of 2-qubit gate operations that you can do in this system actually per coherence time of your qubit electron spin is larger than the number of operations that you can do for superconducting qubits. Of course, this platform has not been scaled yet as well for the reasons that I'll mention in a moment. But once it scales, you can build larger depth quantum circuits because you can do operations at gigahertz speeds, these optical spin rotations, and coherence times can be very long. So what is the problem? Well, these systems are smaller by a factor of about 1,000 or even larger because you work at optical frequencies. So you have to rely on sophisticated fabrication techniques to build the system. Everything is much smaller. And also your qubits are impurities that you have to incorporate by implantation or some other tools. And that's, of course, much harder than lithographically defining the qubit. But, once you have everything done, then there are these advantages that are certainly major advantages in terms of building scalable systems. So the effort is definitely worth it. So how do we work on this? How do we address all of these issues? Non-sophisticated fabrication techniques. How do you incorporate these kind of individual impurities and atoms inside of a semiconductor at controlled spots and without affecting the environment? And how do you build everything that's a factor of 1,000 smaller than for superconducting systems? I mean, that's something that I'll be telling you about now. And again, for us, the materials of choices are diamond and silicon carbide. So first, in diamond, we primarily work with 2 different types of impurities at the moment, silicon and tin vacancy color centers. And these are basically just 2 missing carbon atoms with an extra silicon or tin atom in between. For silicon, that's an effort that has been done over the past 10 years or so by many groups around the world, including us, and excellent photonic interface has been demonstrated, and also interaction between 2 different qubits inside of the same cavity at Harvard. But recently, we and others have moved more towards tin vacancy color centers that you see here, which are basically the same as silicon, the same group 4 impurity. But the reason why they're more interesting is because they can enable operation at somewhat elevated temperatures, because you have larger ground state splitting. So you are not really affected by phonons at temperatures of few Kelvin. And they also have higher internal quantum efficiencies than silicon vacancies. So in principle, you should achieve all of the advantages of silicon vacancies that are somewhat leading kind of qubits for implementation of quantum technologies in the car centers world for the past 10 years or so. You could implement all of those advantages using thin vacancies, plus operate in at higher temperatures in closed cycle cryostats and have higher efficiencies, which is of course crucial for scaling. And recently we demonstrated excellent quantum photonic interface for this. I'll say a few words about that in the moment. And then in collaboration between the groups of Mette Ataturre in Cambridge and Dirk England at MIT, they've also demonstrated optical spin control and excellent spin properties of these qubits, putting them on par with silicon vacancies and proving that indeed their properties are exactly the same, but at elevated temperatures, which is actually very important for these experiments. So dilution refrigerators are not needed for thin vacancies. The other set of qubits that we're interested in are related to impurities in silicon carbide. So these are again optically addressable spin qubits in silicon carbide. And there are many different color centers that people are studying here. My group in particular has looked into silicon vacancy in silicon carbide in 4H polytype. And again, silicon carbide has many different polytypes, which are different arrangements of silicon and carbon atoms. But we're interested in silicon vacancies, which are just missing silicon atoms in this particular polytype. And you see here that they have very nice properties and have also good coherence times that have been demonstrated. And there has been a lot of effort on that, but there are also some other exciting impurities or defects in this material that other groups are studying around the world. And I should also mention that silicon carbide as a material is interesting because it's much cheaper than diamond. In fact, it's a material that people use as fake diamond in jewelry. So it's much cheaper. You can get it on wafer scale from companies. You can also, people use it even in abrasives and sandpapers. Fake diamonds are here, heating elements, power electronics. People can make power electronics there, use it for some sensors, MEMS devices, for harsh environment, for space exploration, for example. So it's a much more mature and less expensive material than diamond. And it turns out that it also hosts these color centers that are on par with diamond color centers, which is why we're very excited about it. You know, I'll show you in a moment that, you know, it's really kind of in terms of research these days, kind of on par with diamond. But before I get there, let me explain what the main problems with these platforms are. You may wonder, well, you know, this is all interesting, but why people haven't scaled these platforms up as much as they have superconducting qubits. And the problem is, again, in the fact that you have to incorporate these individual atoms and impurities inside of a solid in such a way that you don't damage the solid itself. That's why there is a lot of exciting work, you know, in Sydney on really doing atomic force kind of scanning microscope, kind of tunneling microscope arrangement of atoms inside of a material, right? But we're trying to also do it by implantation or incorporation in such a way that we don't damage the environment, because ultimately you want to have your naturally trapped atom or ion inside of a semiconducting or solid environment. And that's, you know, very hard to do. I mean, nothing is perfect. You always end up with some inhomogeneities. Even if you have the best process, you always have some spatial inhomogeneities, right? You know, you can't always with 100% yield incorporate these impurities at desired spots. Or you have some spectral inhomogeneities, which would come from basically some imperfections in the surrounding environment, because this is not anymore atom or ion in vacuum, right? It's beautiful that you don't need to trap it, but there are phonons, there are other atoms, so that anything, any damage, any strain, any imperfections would lead to change in the transition of that atom and inhomogeneous broadening. But at best, we can actually reduce this inhomogeneous broadening of the transitions to about 30 gigahertz, which is still something that, as you'll see in a moment, we can control with a variety of tuning methods. So of course, we and the whole community spent probably past decade or even more trying to control these spatial and spectral inhomogeneities. How do you incorporate these atoms and ions at desired spots with maximum yield? How do you control this, minimize this inhomogeneous broadening so that all of your qubits are homogeneous and can talk to each other? And in this effort, first for reduction of spatial inhomogeneities in collaboration with Ziad Shan and Nick Melosh from Stanford, we developed this shallow ion implantation and subsequent diamond overgrowth method, which is basically the method that uses very low implantation energies to incorporate these impurities in diamond in order to minimize damage to diamond. So it's different from traditional approach that you use much higher energies. So then we use very low energies, which leads to these ion, and then we can also use masks to incorporate them at desired positions. But of course, your tin atoms or silicon atoms end up being very close to the interface, which means that you have to regrow high purity diamond on top. We managed to perfect this method so that we right now have these impurities implanted by these methods that are comparable in properties to even naturally occurring impurities in the material or CVD grown ones. And we can incorporate them at desired positions anywhere we like, even in the shape of my group's logo, right? This is luminescence from tin vacancies on a chip. I mean, it's not really useful for anything, but it shows you that we can completely control their positions. And then for spectral tuning, we developed a tool set of different techniques, and there are even others beyond the ones that our group has developed, but we recently primarily focused on electrical shifting, stark shifting of these color centers, and we can do that for silicon carbide color centers. Here you see how we can tune stark shift by putting electrode and applying voltage. The color center transition by a few hundred gigahertz and compensate for all of inhomogeneous broadening. And color center transitions are still stable over hours time scale. So that's really good. It's not degraded in the process. And the same type of stark shifting also works for color centers in diamond, as we recently showed for tin vacancies in diamond. So we, basically have all of these techniques that we can use. Nothing will ever be perfect. We will use some alignments of the structures and some spatial growth at desired positions and spectral tuning to overcome spectral and spatial inhomogeneities and build scalable systems. But of course, people do that in all the other systems. Nothing is perfect. Atomic systems are not perfect. Superconducting systems are not perfect. People have to use post-tuning methods to compensate for all of these different imperfections. And even more recently, we started looking into kind of more complex tuning of these color centers to overcome inhomogeneities. So it's not just a simple stark shifting with the DC signal to tune the transition, but also optimize the driving on the transition to control the output spectrum. So it's related to the idea of loci engineering, so that you can completely control the spectrum of your color center at the output by applying particular driving microwave signal. And this was done in silicon carbide, but of course it's applicable to diamond as well. So now, that's one piece of the puzzle, right? You want to have your qubits, which are homogeneous and that are also long-lived and so on. But you also want to have efficient connections, right? And you want to map the state of those spins to photons, but also collect those photons and use them to interact and build a scalable system. And for that, we rely on our inverse design. That's what I was talking about in the first part of talk. We have to build photonics in these materials, both diamond and silicon carbide, but then we also have to design efficient photonic components and often components for some new functionalities. So how do we do that? Well, I mean, if you're familiar with photonics, you know that for photonics and on-chip photonics, you need some high index material sitting on insulator, and then you can guide light and process it. And that's why silicon on insulator has been really successful in terms of building integrated photonic systems. But of course, that's one material. It's not really working well for a lot of applications. You need a lot of other materials. And recently, lithium niobate, thin film lithium niobate on insulator was also commercialized, and a lot of people do photonics in this material for optical switching and nonlinear devices. And silicon carbide, for example, although I advertised it as widely available material, doesn't really exist in this form. When you buy it in a bulk form. Same thing with diamond. It's more expensive, but when you buy it in a bulk form. So how do you make like these thin film structures or guiding structures in these materials? So what we do is we do three-dimensional bulk carving for diamond, and literally we carve out these structures that are suspended in diamond, and you see some inverse designed elements there. And we do it in such a way, we etch down and then undercut sideways and still keep color centers inside. And in silicon carbide, what we do is basically we make silicon carbide on insulator ourselves and then make photonics. And I'll show you some of the recent results in these materials that are quite exciting. And what is also very important is that these processes are fully compatible with our inverse design. So now with diamond, you see these inverse designed elements here that we optimize and also carve it this way. And I should say that the method that we used was actually pioneered by Paul Barkley from University of Calgary, but it's used by us and also Dirk Ingund and MIT and many other groups now. So it's really a beautiful method of three-dimensional bulk carving that is compatible with also optimized structures and works really well because optimized devices can lead to much higher efficiencies relative to traditional approaches, same as in silicon. I mean, this is just comparison for a very simple coupler, but we've done other elements as well. So recently, we've also shown that you can implement these photonic structures and also have thin vacancies inside of the structures and not degrade their properties and have excellent photonic interface. So that's example shown here, diamond cavity with high Q factor, thin vacancies inside. And of course, that's very important because when you make photonics for quantum applications, you don't want to affect the properties of your color centers. And then when you tune your cavity across transitions of your thin vacancies, you see them light up because you have large Purcell enhancement. And as of now, we have Purcell factor of around 25, strong spontaneous emission rate enhancement. And we redirect most of the emission into a single mode that we can collect, which is very important. This is state-of-the-art 14 vacancies in diamond, and that was published very recently by our team. And also very soon after that by the group of Marco Launcher at Harvard, but it's a very important step towards building scalable systems with this. So all the pieces are there. We know that we have good spin coherence for thin vacancies in diamond. We can make photonic structures and we can scale it up, and now we can move on from there. We also know how to adjust them on resonances with each other. And in silicon carbide, it's the same story, but of course, when you start from bulk silicon carbide, you either do three-dimensional bulk carving, which we tried, but then we also came up with another idea that works even better for silicon carbide, which is just bond silicon carbide on oxidized silicon, grind thin until you obtain thin film, and then use that thin film silicon carbide to make your photonics. So it's really grind and polish method, which brings you from here to a chip that works really well, something like this. And with that, we can also build very high quality photonics, very high quality factors of resonances greater than 5 million. Loss, this is in telecommunication units, but it's actually comparable to lowest loss photonic structures made in foundries for silicon nitride. And we can also have inverse design structures and color centers inside and build scalable systems. So it's actually even better than silicon photonics, which is kind of state-of-the-art photonics that is done in the foundry. This one actually has even lower loss than silicon photonics. And what is also very important is that once you have silicon carbide on insulator, process for fabrication is exactly the same as for silicon. So that's quite exciting and also hosts very high quality for color centers. So again, here is our silicon carbide photonics with very high quality. It has very high Q factors. It's also very interesting for nonlinear optics. You can demonstrate high Q factors. You can put inverse design structures. You can even build solitone combs, frequency combs that are interesting for metrology, as we've done with comparable properties to other materials. This is actually more work on solitone combs and characterization of solitone combs in this material. And finally, you can preserve color centers with great properties that are well coupled to the structures. So now, that brings me to the very end of the talk. Now the question here is, okay, this is all the elements seems to be there, but how do you go from here to scalable quantum systems, right? How do you put everything together and have thousands or even millions of elements that are interacting together? Because, there are elements and they can be tweaked and tuned on resonances, but it looks quite complicated, because even if you have thousands of them and you need to tweak them individually, this seems pretty complicated. And that's true, but that's the case also in other systems like superconducting systems. All elements have to be controlled and tweaked individually, which is why we started thinking about other approaches, whether we could actually, instead of kind of this simple approach where each qubit is individually controlled, to bring them all on resonance, which really becomes very complicated beyond few dozens of them or few hundreds of them. Can we actually kind of get rid of most of these control elements, kind of think in the same way we're thinking about the inverse design photonics? Can we make structures where we can replace hundreds of these electrodes with just one set of electrodes and kind of optimize the signal on them so that we control them all globally somehow and make things that are much simpler? And that really brought us into kind of same type of thinking that we apply to photonics problems, but now we started applying this to quantum problems, right? And in photonics inverse design, what we really do is we couple electromagnetic simulator to optimizer, fast optimizer, to search the full parameter space in 3 dimensions to produce photonic device. We started thinking recently whether we could actually have optimizer, same optimizer, kind of gradient descent tool, coupled with open quantum system simulator instead of electromagnetic simulator, so that we could really optimize the system to exhibit particular Hamiltonian, right? And this means really maybe optimizing driving on the system or optimizing geometry on the system in such a way that you can do this in a simple way and scalable way. And so far, we actually started really doing this, coupling open quantum system simulators with optimizers to solve kind of in a simpler way, simple problems of driving on systems consisting of multiple emitters. For example, in the context of quantum transduction, when you have a homogeneous system, that reduces the efficiency of your transduction from microwave to optical signal dramatically. But we thought whether we could actually apply some global signal instead of tuning all of these color centers on resonances with each other, so that with that global signal that is having some optimized drive applied to that, we could recover homogeneity at some level and improve transduction efficiency. And indeed, we've been able to do that. You see here that for optimized system, we can actually improve this significantly relative to unoptimized. And we can actually improve by a factor of about 20, right? So you kind of, this optimized drive recovers at some level homogeneity. Also in theory, we looked into other problems like problem of multi-emitter systems where optimized drive can recover kind of super radiance in the system. If you have cavity and multiple emitters that are not coupled to the cavity, can you kind of drive them instead of tuning them with DC signals on resonance? Can you recover their collective coupling and super radiance by applying some global drive and recovering that coupling? And we've shown that that's also possible for multi-emitter system and some optimized drive applied. And we just posted a paper actually last week or a few days ago where we showed that indeed we can recover super radiance in inhomogeneous systems, realistic inhomogeneous systems, just by optimizing the drive on single set of electrodes or single optical drive. And you bring your system closer to the ideal homogeneous system, right? So your eigenstate super radiance is recovered to some level, which is important because it means that you don't really necessarily have to tweak each of your 1,000 qubits or millions qubits of qubits. Maybe you can actually replace many of these electrodes by a single set of electrodes and apply optimized signal and still recover some of the homogeneity and super radiance and entanglement in the system. So that's where we're going. That's kind of a merge of kind of open quantum systems and quantum design with optimization tools. And I like to just finish by summarizing that really photonic optimization is crucial for implementation of classical and quantum photonic system geometries, but also beyond that photonic optimization, we're also thinking about quantum system optimization by replacing electromagnetic solvers with open quantum system solvers. And finally, we're thinking in the context of quantum systems about 2 different sets of materials, diamond and silicon carbide. But for classical photonics, we're working primarily with silicon and traditional foundries, commercial foundries. But of course, this is applicable to any materials of your choice. And with that, let me thank my group and my team, and thank you very much for your attention, and I'd be happy to answer any questions you have.
Do you have any questions? Please just go and ask.
On the first part or second part or anything?
I have a question. So when the impurity, so it's how to control that only one impurity is embedded in three-dimensional media. So it's not, it's not on the surface. It is somewhere in.
No, it's somewhere inside. I mean, the experiments that I've shown with the start shifting basically mean that you put electrodes, right, and that there is some field distribution between your electrodes which affects impurity, right? And you can do start shifting, or you can drive it with a laser and do some Raman type scattering or tuning. But of course, when you think about having several of them or hundreds of them or thousands of them in a small volume, that approach is not working anymore, because it means that each one of them would have to have a separate set of electrodes. And if they're in the volume of a few hundred nanometers, like 5 of them, you can't control them individually. So the work from Harvard, where they showed entanglement of 2 color centers to the cavity, they could control them with the external magnetic field. But that's, of course, not applicable in a general case, because for arbitrary set and larger number, you can't do that. So what we're showing is that in principle, with a single set of electrodes, you should be able to recover some of the homogeneity if you go beyond DC signal kind of driving the system and tuning the system, but instead you optimize the drive on that electrode. Kind of you have multiple harmonics that are all producing different Folke eigenstates on those color centers and making them interact.
Okay, thank you. We have a question from Augustine. Augustine, please go ahead.
Yes. Hi. Can you hear me?
Yes. Hi.
Yeah. Thank you for a very impressive talk.
Thank you.
I have 2 questions that might be naive. One is regarding your optimizer. I don't really understand the architecture. Do you see there an opportunity to have, for example, trained convolutional neural networks as a means to achieve this very non-intuitive structure?
Yeah, definitely. I mean, there is a connection to neural networks, because the problem of adjoint optimization is very similar to back propagation in neural networks. So adjoint optimization basically means that you're calculating gradients from 2 simulations, forward and backward simulation. And there are papers that people have published on the connection between adjoint optimization and actually back propagation. It's pretty much mathematically the same problem. So now the difference, kind of subtle difference, I mean, and people have also applied training of neural networks to do photonics design. So now, I mean, this is maybe different, the differences in details, right? Generally, when you think about training neural network, you need a large set of data in order to train it to solve a particular problem, right? That is possible, but the problem is that when you go from one photonic device to another, what we've noticed is that the space is completely different. So you need to retrain the problem. And also parameter space is so large that you need such a large data set to train this that, generally that approach of just using convolutional neural networks works best if you have smaller photonic structures. If you have something large, then it's not as time efficient as traditional kind of gradient descent type of optimization. But having that said, the way we do optimization, gradient descent still has connection to back propagation, because the way we calculate gradient is from these forward and backward simulations. So you are sort of, as you are doing gradient descent as solving problem, you're kind of, doing some sort of training. And we've also shown that we can accelerate that gradient descent by kind of training our electromagnetic solver to find the right basis to solve the problem.
Thank you. Then my second, I see. So my second question is regarding what kind of output you might have for this on-chip architectures. I mean, are you interested, for example, in optimizing the output of your light, for example, in terms of polarization or spectral phase?
Yeah. Yeah, that depends on the, that's certainly possible, right? So, you know, I showed initially some examples of those different angular momentum modes, for example. I mean, that's not something that we're using in the context of quantum systems or photonic systems, but in principle, you know, your inputs and outputs, you have a black box that you're optimizing, right? And your inputs and outputs are well-defined modes, right? So whatever you would like to have as your input, you know, it could be mode in some waveguide or free space mode, and your output is a particular polarization or particular mode, again, in free space or a waveguide. You're optimizing the medium, like the black box in between, to have that input to output mapping, right? Which means that you can pick whatever you like as your input and output modes. And then, of course, you can pick whatever material you like for and whatever material you can process for your medium in between. But certainly, you know, if you have an idea to use a particular modal basis for solving your problem, you can design elements for that modal basis. So, for example, for our multidimensional communication problem, we do use a specific modal basis in a waveguide, right? But we also showed that it could work with this angular momentum basis. It works in on-chip configuration, but also in a free space configuration, right? The problem of these angular momentum modes had on-chip input and free space output, but you can also have free space input and free space output. Again, this is a very general tool, right?
Well, thank you very much.
Thank you.
We have two more questions. One from Angelina. Please go ahead.
Yeah.
Thank you very much. And also thank you very much for the great talk.
Thank you.
I would like to ask something about the inverse design structure, namely, and maybe you have mentioned that, but how interesting and realistic would it be to think about like dynamically switchable architectures?
Oh yeah, definitely. That's an excellent question, right? And we're doing some work on that, right? And the way we're doing that, and this is completely doable with the current software or the current tool, right? When you think about dynamically switchable structure, right, you are always switching something, let's say refractive index, right? But in most structures, you are basically not changing geometry, you're just changing index of refraction by free carrier injection of some nonlinear modulation. Of course, there's slowly reconfigurable systems with MEMS, right? That's where the geometry changes, but that's a different class of problems. But for fast switchable devices, in general, it's refractive index switching, which means that the problem of designing a dynamically modulated device means that you need to design a particular geometry in such a way that for two different steady states, meaning the same geometry, two different refractive indices has different response, right? Like in one case, switches to one port, in other case, switches to other port. And that is something that we're doing and designing already, right? And in terms of mathematical kind of complexity of the problem, it's equally complex and equal size of the problem as doing it for multiple wavelengths, right? The solver doesn't care if you're designing the problem for two wavelengths or for two different refractive indices in the same geometry. It's the same thing. You're handling the same number of matrices at the same time. So the bottom line is absolutely this is possible, and we've done that in the context of modulators, Mach-Zehnder modulators, but you can do it for any other switchable device.
Okay, thank you very much.
Thank you.
Thank you. Do you have any other questions? Please just go ahead and ask.
Yes, hi, hello. I have a small question. First of all, thank you very much for your talk. Very impressive.
Thank you.
And so yeah, I have a question because as far as I know, reciprocity of light wave is a problem, at least for integrated classical photonics, at least for some application. And I was wondering if you could comment on this.
Yeah, definitely. So that's an excellent question because I mentioned non-reciprocal devices in passive silicon photonics, right, that we demonstrated. And this was done in collaboration with Andrea Lu from City University of New York and Shanhui Fan from Stanford. So what we demonstrated was not a full isolator, complete isolator, like what would require magneto-optic materials and so on, which is a very difficult problem and kind of holy grail of integrated photonics. But what we have demonstrated is a system, and this was based on the theory proposal and microwave demonstration by Andrea Alu's group. We demonstrated a system where you can achieve non-reciprocal transmission by combining nonlinearity and particular response function of the system. So it's basically the system consisting of two resonators with Lorentzian and Fano response, and one Fano resonator has nonlinearity, and you design the system in such a way that in forward and backward propagation direction, you couple different amount of power to nonlinear resonator, and that shifts transmission in different directions for forward and backward propagation, which means that you have non-reciprocal transmission at the target wavelength. Of course, it's not a full isolator, and it turns out that it works in a certain dynamic power range, and it works, we showed non-reciprocal behavior for kind of 10 gigahertz operation with pulses, and it has very small footprint and low power consumption. So it works really well as kind of substitutes isolator for example, ranging measurement in LiDAR, but it's not a full isolator. So if you're interested, we had a paper in Nature Photonics last year, again, with our collaborators, and it's based on a proposal from a few years ago. But what inverse design enabled is doing this at optical frequencies as opposed to microwave demonstration, which was done a few years ago.
Aha, okay.
Yeah, so it's really based on nonlinear systems, yes. I don't know if you're familiar with those proposals, but that's what it is.
No, but maybe I should have a look, because I thought, okay, maybe a related question.
Yeah.
Because there has been some development in the past years in a field called topological photonics.
Yes, yes.
And I was wondering if you think that, okay, typically you can achieve some kind of chiral mode for light in some proposal at least, and I was wondering if you think that this direction is interesting for some application, or maybe not.
Yeah, it is interesting certainly, but for a limited number of applications, right? So even I think what we demonstrated at some level has a relation to some of the experiments that people have done in topological photonics. I mean, if you think about the demonstration of our system, and if you look up the paper, I mean, it doesn't really work if you in a isolator. When you think on an optical isolator, you know, if you shine a light from at the same time continuous wave signal in the forward and backward direction, it should still block the backward signal, right?
Yeah.
That's not what our device does. It wouldn't work if you shine continuous wave signal in both directions. And same thing for topological photonic demonstration. So it's not really an isolator. But it works in the regime, in a specific regime, when literally, you know, you in a pulse regime that I described, and for particular pulse duration, which is related to kind of delay, phase delay between the two resonators in the system. And that means that it kind of works really well as a substitute for isolator in applications like a ranging measurement, where you're sending pulses, reflecting them back and sending them to detector, and you don't want them to end up in a laser. So there it substitutes isolator, because you will never really have, extremely unlikely to have your signal at the same time at the input and output port.
Uh-huh. Okay.
Yeah, so it's again a limited number of applications.
I see. Thank you.
But it's worth it because it's much more compact and has high efficiency and fully passive, and it's all silicon, right? So if you're building a LiDAR or doing any type of range measurement, you don't need to build an isolator.
Mm-hmm, mm-hmm. Okay. Okay. Thank you.
Thank you.
Thank you. Any other questions? Please just go ahead. If not, let's thank you, the speaker, for the great talk.
Thank you. Thank you all for the invitation, and it was great seeing you on Zoom. And thank you, Dimitri, again for the invitation. Thank you. Bye.
Have a nice day to everybody.
Thank you, likewise. Bye.
Thank you.